Now, we're done with the long reaction stereochemistry of nucleophilic substitution. Let's proceed with a very short part for the reaction stereochem of elimination. And actually, we just follow one simple rule for that. It's Zaitsev's rule. And this is actually the counterpart of Markovnikov's rule in elimination. And we'll see why. For example, I draw a certain RX compound. Let's just use an alkyl halide, perhaps, something like this. Alright. Now, what if we add a base here? A strong base. Of course, we're going to have elimination in this case. Thing is, we have here the alpha carbon, and since this is beta elimination, the base will pick a beta hydrogen from this beta carbon or this. Now, the question is, which of these two carbons will the base pick? The one at the left or the one at the right? The quick answer to that is both. But which of these would the base prefer to pick more than the other? Well, the rule is that, in Markovnikov's rule, the rule is, in one way, Markovnikov's will pick the more stable carbon beside the alpha. And if we apply that here, we say that the beta carbon that is more stable will get the double bond. This is kind of different from how Markovnikov's rule is explained, but actually the principle in concept is very much the same. So look at here. Well, the carbon here is not supported by other carbons, whereas the carbon here has two carbons, making it more stable. So meaning that this is the carbon that the base would prefer to snatch a hydrogen from, because the carbon here will be like, okay, take my hydrogen away, I'll be stabilized anyway by these carbons. Unlike here, this one can't afford to lose hydrogens because it will be very unstable if the base does snatch a hydrogen from it. So meaning, we have two potential products. If the bond will be between this one and this one, we have this product, and the other product will definitely be having the double bond between these two carbons. So since we say that this is the one that would be preferred by the base, this would be the product from that, this will be the major product, and this would be the minor product. Let's say around 80 to 90 or to 90 something percent of the products would be this, and a very small part of the products would be this minor product. And so that's it for the reaction stereochemistry of elimination. Now, for the last part of generalities in RX compound reactivity, we are going to see a competition between elimination and nucleophilic substitution. Now, why is there going to be a competition between the two? Let's give an example of a base, NaOH, sodium hydroxide, caustic soda. We know that this is a very strong base, even from our general chemistry days. But the thing is, if we go back in SN2 reactions and we refer to a strong nucleophile, NaOH would actually qualify as a strong nucleophile. So meaning it can be a base, but it can also be a nucleophile, a strong base or a strong nucleophile specifically. So meaning at one point NaOH could be a base, and at one point NaOH could be a nucleophile. But when will it become this, and when will it become like that? Well, let's analyze first what's happening between what's happening in elimination with contrast, or in contrast with substitution. So I'm going to try to find a certain reaction here. Alright, let's go back to this. You can see that in an elimination, there's a breakage of one bond, that's a leaving group. Then the snatching of the hydrogen, that's another bond breakage. Then you're forming another bond, So you can see there's a lot of energy being required in elimination as compared to, let's say here we have an SN2 reaction. Nucleophile comes, leaving group goes, reaction is done. So it's not as energy intensive as in elimination. So what do we say? We say that elimination is more energy intensive. And since in the laboratory we refer the energy here as heat or thermal energy, we're going to talk about temperature. So meaning if elimination requires more energy, elimination would actually be preferred in a higher temperature. So this means to say that if the temperature is high with a certain reagent that could act as both a base and a nucleophile, the reagent will actually become a base because it will now prefer elimination. So elimination is preferred. Whereas if the temperature is lower, the elimination is less likely to happen, but the nucleophilic substitution will stay and it will prevail as the major reaction. And basically that is the main condition being required. Alright. Now, let's go to specific reactions of the RX compounds. Let's start with the alcohols. Actually, the reactions are very basic. For example, I draw here ethanol. If we want to turn it into alkyl halides, we have two options. As usually stated in the books, if we want to turn an alcohol into a bromide or an alkyl bromide, so we want an alkyl bromide, we use PBr3 or potassium. No, what potassium? What the hell? Phosphorus tribromide. That's disgusting. Alright, it's not potassium. Okay. Anyway, now if we want to produce a chloride, we use this reagent SOCl2. This actually has a quite a unique name, thionyl chloride, and we will actually encounter thionyl chloride later on again. Now there is something even more than just that simple, more than just these simple reactions, and that's redox reaction. If you recall, back then in alkenes we have strong oxidation, wherein from a certain alkene we produce something that is said to be oxidized, and in order to show redox in alcohols, let's draw the line formula of ethanol. And let's look at this alpha carbon right here. It has two hydrogens. If we go back to alkenes, we could actually refer back to this as oxidizable hydrogens. So there's a certain, so this is, we say that the alcohol is the most reduced form when we talk about oxygen containing functional groups, because here we have OH, then we have two hydrogens. Can it be something more reduced than that if we talk about anything with oxygen? If we oxidize it weakly, this is my symbol for oxidation. If we sacrifice one of these hydrogens, what happens? Alright, just like in strong oxidation, if we have a hydrogen here and an oxygen bonded here, the oxygen here could take away this bond in order to form two bonds to itself. So this C to H bond will be sacrificed and will be given to OH. After that, the OH will now have two bonds to this alpha carbon, and then this hydrogen remains untouched. So after weak oxidation, what do we have here? We have a C double bond OH. We have here a formyl group, right? And this is the functional group for aldehydes. So meaning, in a partial or a weak oxidation of alcohol, we have here an aldehyde. But take note here that we have a certain alcohol here. This is the alpha carbon. It is attached to one carbon. Take note that the aldehyde is a product of partial oxidation of a primary alcohol. Now, why did I mention that in the first place? What if we use a secondary alcohol, such as this? We know clearly that this is isopropyl alcohol. Let's try to oxidize this one. Alright. By the way, the reagent for partial oxidation is PCC or periodinane. They're not the same. PCC is another compound. Okay. Now, if we use PCC or periodinane, we will have it undergo weak oxidation. Or even if we use the strong oxidizing reagents such as anything with chromium, that is potassium chromate or potassium dichromate, we will come up with the same product. Here, the ketone has one hydrogen left. That is the reason why if you oxidize a secondary alcohol, what will happen? Of course, nothing happens to this carbon and these hydrogens. Now, the hydrogen will be sacrificed and will be given, and this bond will be given to the oxygen. So just like in the aldehyde, we will now form two bonds for the oxygen here. And what do we have here? R, carbonyl R. This is actually a ketone. So meaning that the ketone is the product of oxidation of a secondary alcohol. It doesn't matter if it's weak or if it's strong oxidation. As long as you oxidize a secondary alcohol, you will produce a ketone. Now, the ketone cannot anymore be oxidized, but the aldehyde can. And that's because the aldehyde still has one H left that can be used for further oxidation. And if we do oxidize that further, what happens? The H will be replaced by OH. And if we replace the H with OH and we copy everything else, what do we now have? We used to have a formyl group here, CHO. Yeah, that's correct. We now have a COOH. We have a carboxyl group here, and thus we now produce a carboxylic acid. And meaning that from a primary alcohol, if you oxidize it strongly, this is strong oxidation with the use again of chromium containing compounds such as potassium dichromate or chromic acid. Okay, we will now produce a carboxylic acid, and this is the most oxidized version of the product from a primary alcohol. Now, when we talk about alcohols again, I want to mention one property for them that's kind of special before we move on to amines. We have here an alcohol. Actually, I shouldn't have drawn the line formula. It doesn't matter. Well, I'll just draw it to make it complete. We have this alcohol. Then let's draw the same thing. CH3, CH2, then OH. It's not the ideal drawing, but the point I want to put here is we have here an OH, which is, we know, a polar functional group. If we have a partially negative O here and a partially positive H here, which is bonded to another electronegative atom, which is O, they can form what? This is a hydrogen bond, if you recall. And the hydrogen bond is the strongest force of attraction among those present in organic chemistry. So what do we say again? As the strength of the force of attraction increases, the melting point and the boiling point increases. So meaning that alcohols tend to have a high boiling point. Sure, you may say, hey, how could you say that? Methanol and ethanol are, common in the laboratory, and they quickly evaporate. They're quite volatile. All right. So if they're kind of volatile, how can you say they have a low boiling point? If you heat the ethanol, it will evaporate very quickly. But the point is, this is in comparison to alkanes. In comparison to other compounds, such as hydrocarbons, if the alcohols volatilize quick, the hydrocarbons, such as, for example, if you expose hexane in the laboratory, which you should not do because it's carcinogenic. But anyway, if you expose hexane and an alcohol at the same time, if you expose an alkane and an alcohol at the same time, given that they have the similar carbon lengths, the alkane should evaporate faster than the alcohol, because the alcohol has higher boiling point due to hydrogen bonds. Alright. So that's just something I want to catch up with in discussion of alcohols. Now, let's go to amines. Well, amines generally don't have specific reactions in organic chemistry that I would like to emphasize. But I would just like to emphasize that if alcohols here, they have this property to have hydrogen bond, amines have a certain property as well. For example, let's have an R here, then an H, then two H's here. So this is a primary amine. This is a primary amine simply because the N here is attached to one R group. And if you have two R groups, then I think you know what's the trend. This is secondary, and this is tertiary. Now, we know that nitrogen actually has one lone pair, and the thing is, as compared to oxygen, nitrogen is less electronegative. So meaning nitrogen as compared to oxygen is like, hey, I have lone pairs. Yes, I am electronegative, but as compared to oxygen, I can give them more freely. And since this is an action of electron pair donation, by Lewis definition, this is a base, because an acid is an electron pair receiver or acceptor, and a base is an electron pair donor. Now, the next question is, which of the three is the most basic, and how's the progress? What's less basic after that, and what's the least basic of the three? Well, thing is, technically you want a nitrogen that is very stable enough that it would freely give out its lone pair. So you would expect that here the tertiary amine would be the most basic because it's the most stable nitrogen here. It's going to be the one which would give away this electron, because nitrogen's like, hey, I could give out this lone pair because these R groups are just giving me electrons, so I could let go of this. And as compared to this one, nitrogen here is, okay, I can give away the lone pair, I have two R groups. And here nitrogen is like, no, I can't freely give out this one as compared to the other two because only one R group is supporting me. But the thing is, here there's a kind of problem because we encounter a certain incompatibility here. There's a steric effect here that prohibits or inhibits the nitrogen from giving out its lone pair. So technically, this one is less basic as compared to this one. So what do we mean? We say that the secondary amines are the most basic, followed by the tertiary because they're stabilized anyway, but they have steric effect, that's why they're less basic. Then we already know why the primary amine is the least basic of the three.